I'm Sam. I'm a thermal engineer based at REL Space, and for this week's REL Talk, I'm going to be discussing the SPICE thermal design, or more specifically, how that thermal design is holding up since the launch of Solar Orbiter last year. I'm going to start by giving a very quick overview of the thermal design. I'm then going to talk about the verification process that we performed at REL, and then I'm going to finish by talking about the flight telemetry and what that's showing us. So I'm sure many of you are already familiar with Solar Orbiter. It's an ESA mission that launched in February of last year. SPICE is one of 10 instruments. It's located in this top right-hand corner of the spacecraft behind the spacecraft heat shield. And it's a high-resolution imaging spectrometer that operates at extreme ultraviolet wavelengths. It was built by a large international consortium of organizations based both in Europe and the United States. And it was delivered, led by REL and delivered for integration to the spacecraft back in 2017. So before I start talking about the thermal design, it's worth talking about the solar environment. So Solar Orbiter ultimately is going to reach a perihelion of 0.28 AU. And at these solar distances, the solar flux is approximately 17 kilowatts per square meters, or around 13 times what you would see on a typical Earth orbiting satellite. The main inputs into SPICE is via a relatively small, roughly 40 by 40 mil aperture. And it's worth bearing in mind that this solar load has to be managed alongside a host of other thermal design challenges, notably a requirement to cool our detectors to minus 20 degrees Celsius, manage the heat loads across the interfaces with the spacecraft, and minimize thermoelastic deformation. So I could very easily spend all day talking to you about these various challenges and how we tackled them. Really, the focus of this talk is on the solar environment and how SPICE deals with that. And this slide really shows that. So we've got a couple of CAD images of Solar Orbiter here. This is the door mechanism that opens when we operate with the 40 by 40 mil aperture. And the incoming beam passes through this left-hand side of the instrument. It bounces off the primary mirror, through an insert in the central baffle, and it then reflects off the grating assembly where it diverges into two separate beams of different wavelength bands, and then it impinges on the detector assembly at the far end. So really the thermal design comes down to this primary mirror, which is designed to be reflective to the ultraviolet wavelengths that we're interested in for the science, but transmissive to infrared and visible. And what this means is that the majority of the incoming flux passes through the mirror. So this is about 2/3 of it that passes through the mirror and reflects back out into deep space via this periscope type mirror at the back called the heat rejection mirror, which we can see in a bit more detail here. Of what's then reflected back towards the far end or the front end of the instrument, we have these pre-slip fold mirrors which prevent heat from being absorbed by the central baffle, and instead reject that light onto the heat dump radiator, which re-radiates it back into the spacecraft cavity in a very controlled way. So as I said, a lot of this comes down to the primary mirror. The mirror itself is comprised of a synthetic quartz mirror. We have an aluminium mirror mount, and then the whole assembly sits on top of a scan focus mechanism, which aligns the mirror as we need it to. What gives it its unique thermoptical properties is the boron carbide layers. There's a small thin layer of coated boron carbide in a square on the front surface of the mirror. You can't really see it in this image. So it's this coating that gives us the reflectivity at UV and the transmissivity at visible and infrared. This coating was qualified by the Max Planck Institute for Solar System Research, and they provided us with this set of characterization data which shows the various properties at different wavelengths. You can see at the lower wavelengths at the UV level, we have a relatively low level of transmission and a relatively high reflectivity. And then as we pass through the wavelengths into visible and infrared, we see the transmissivity increase and then corresponding drops in reflectivity and absorptivity. So really this data was the first step in allowing us to understand how the instrument would perform thermally. And then that led us on to building a thermal model. So this was built using a piece of software called eSatan TMS, which is a finite difference software specialized for use in spacecraft thermal analyses. But then we also had to verify that design. So we had ground testing conducted firstly in 2014 on a test model of the instrument, and then on the flight model in 2017. And that allowed us to refine the thermal model, correlate our thermal model, and improve the confidence that it would give us the performance that we need and that the model would be accurate. We did perform solar simulation, but as you can probably imagine, simulating 17 kilowatts per square meter is not something that's really possible or practical or safe in a typical lab environment. And this was a common issue, I should add, faced across the entirety of the Solar Orbiter project. So for that reason, we used a mercury lamp, which you can see in this image here. That was capable of providing about 2 or 3 solar constants, but importantly, it had enough intensity to drive the gradients through the instrument that we needed to correlate our thermal model. And it had enough light in the UV to get the reflection on the primary mirror that we needed. But there's clearly some uncertainty in that process, both due to the lower intensity and also the spectral differences between the solar simulator and the true solar spectrum that we were going to see on flight. So that leads us on to the launch and commissioning phase. So we had the launch in February of last year from Kennedy Space Center. Commissioning started immediately after, for obvious reasons, being largely supported remotely by the team. And we had the first images in April, which we can see on the right-hand side of the slide at the moment. So that was a really exciting moment for the team. What was perhaps more exciting for me was the fact that also the commissioning provided us with 2 stable periods, one at 0.88 AU and one at 0.54 AU, with the spacecraft and instrument doors open. And this was the first time that we could really see the thermal design in action with a realistic solar spectrum. I should add at this stage, although we're ultimately going to be reaching 0.28 AU, we're not going to get there until the main science phase. So that's from around the end of next year onwards. So over the next year or so, in the course of the last year, we've had a series of Venus and Earth gravity assist maneuvers that have gradually slingshotted us to get closer and closer to our final perihelion. So these 2 opportunities, these 2 periods with the door open, allowed us to compare the telemetry we got from that with the thermal model predictions. We reran the thermal models with the spacecraft interface temperatures that we saw, and we compared the results. So this slide just shows that in a bit more detail. We've got the primary mirror here. This is at 0.88 AU. Primary mirror is this green line. You'll notice that it's already about 15 degrees warmer than the rest of the instrument. The reason for that is that we were actually operating a decontamination heater throughout commissioning, which elevated the mirror temperature above everything else. But yeah, there's really a set of things we're interested in. First of all, the steady state data with the door closed. So comparing this data with what our thermal model predicted at door closed. Likewise with door open, steady state at door open, comparing that with our thermal model. And then the last thing we were interested in was the temperature difference between door open and door closed, and how that compared with the temperature difference predicted by our thermal model. And that would really allow us to more closely examine what the influence of introducing the solar load is on the instrument and how that compares with what we're predicting in the thermal model. So these are the key results. First of all, we've got the steady state data in this table here. So this gives us a measure of the bulk accuracy of the model, and we can see that overall the model is pretty accurate. I'm certainly very happy with this. When we first got this data back, we can see that we lose a bit of accuracy as we get to the closer solar distance, the 0.54 AU. This is true even with the door closed, so even ignoring the solar flux, we have a slight loss in accuracy. I suspect the reason for this is that the thermal interfaces are a bit less uniform. The interfaces with the spacecraft are less uniform, which is something that we can't really account for within the thermal model. When we look at the solar load and the comparison of the flight delta T with introducing the solar load versus what's predicted, we get a slightly more interesting result. It suggests that we're perhaps getting a slightly higher level of reflection from the primary mirror than we maybe would have expected based on our pre-flight predictions. And as you can imagine, for obvious reasons, this is highlighted even more as we get closer. We've got higher solar load, so any existing inaccuracies in the model are highlighted more. I'm not particularly worried about this, the reason being that the primary mirror is the most optically sensitive of the components within SPICE. So the fact that that's not heating up as much as we would have predicted is certainly a positive thing. And it gives us that confidence that the design is going to be suitable when we get back to perihelion, or get to perihelion over the next year or so. So just to conclude, the telemetry is certainly showing that the design is working and the model is fairly accurate, although maybe reducing a little bit as we're getting to this closer solar distance. But we expected that purely on the basis that we had to correlate the thermal model with a lower solar intensity than what we're ultimately going to get to. However, that being said, the flight performance is comfortably within the thermal model uncertainty margins that we calculated prior to the mission. And we fully expect that we'll be within the operational temperature limits comfortably when we get to perihelion. So it's good news. It suggests that the thermal design works. With each orbit, solar orbiter is getting progressively closer to the sun and to that final perihelion of 0.28 AU. And I'm really looking forward to seeing how the thermal model fares as we get closer and the solar load increases. So maybe in another few years, there'll be a further RAL talk on this topic, depending on what the data looks like. So one very last thing before I finish, I've got to give this a bit of a plug. If you're interested in this topic, we actually released a conference paper on this earlier in the week, which we presented at the International Conference on Environmental Systems. It's completely free to view. There's a web page on there that you can go on and you can just search for SPICE and it's easy to find. So yeah, if you want to learn more, there's a lot more detail in there on the instrument background, the ground thermal testing that we did, so particularly the solar simulation that I discussed, and then also the lessons learned overall. Right, so that concludes my talk. Thank you for your attention this morning.